Hey programmers, Alvin here. Right now I want to go over the approach for this tree sum problem. And so in this problem I want to take in a binary tree, just like we've been doing as of late. This time the values within the nodes of this binary tree, they're going to be numbers, right? What I want you to do is compute the total sum of all the values in this tree. So for this example, we should end up with 25. And so hopefully you're kind of gathering how to attack this problem, especially given, the algorithms I've been showing you as of late. So if you've been studying our problems in order, hopefully you know a straightforward solution to solve this one. We could, of course, just use any type of traversal algorithm. So we can use either a breadth first or a depth first traversal, and we can just add all these values into a running sum. And of course, we'd probably initialize that sum to 0. Right? So the iterative breadth first or depth first solution, I think, is very straightforward, right? And I'm not going to really step through that approach with you over here. I think you have that one down pat, especially if you've done the previous two problems. But what I will show you here is actually how to solve this one recursively, which would be a type of depth first traversal, because we know that, hey, depth first traversal relies on a stack, and if you do something recursive, it is utilizing the underlying call stack. So I will get a similar type of ordering. And so when we trace through this type of solution, this recursive solution for this tree sum problem, what we're going to do is try to be very explicit. And I think this is really helpful, especially if you struggle with recursion, right? So given this binary tree, I know that for particular nodes of my tree, like the 4 node, it does not have a left child. Right? And I know, like, programmatically what that means is like that node's .left pointer points to like null, right? It's a null pointer. And so I'm just going to draw that explicitly, sort of like this. Again, that'll just help us really understand how our recursive code performs on this type of input. And so if I know that I can put like a null node to the left of 4, then it could be the case that other nodes, like the leaves of 2 and 1, they also have both left and right children that are also null. So if I drew all of my null pointers explicitly, it would look something like this. Cool. And this is really something that helped me really get comfortable with recursive problems, especially those on binary trees. And what we're doing now is we know that when it comes to solving any problem recursively, it's about writing a base case that is like the simplest version of our input. And here I'm going to argue that our base case needs to be about the null node, right? The null node basically represents no node at all, or represents the empty tree in a sense. In other words, if someone asked me to calculate the sum of a null node or the sum of an empty tree, then to me that sum would just be 0. To write elegant recursive code, try to think about your base case as a problem in itself, right? So if someone gave me an empty tree that is a null node, I would return the total sum of 0. And what that means is I know that all of these null nodes, they would return 0 as their computed sums. Nice. And then from there, how can I use this information to actually build up my main solution, right? So let's go ahead and target this 4 node to the left. And what I have to do is figure out, hey, what is this subtree's total sum? And I can compute that given the values to the left and right. In other words, if I return those 2 null values returns, so they're both 0, now I just have to do 0 plus 4 plus 0, which just equates to 4, right? And that is actually correct in itself, right? So a green number above a node represents the total sum of that subtree. And so it is the case that, hey, the total sum of that 4 node is just 4. And I would do something similar for this node over here, right? When these base cases return to their caller or return to their parent, I just have to add my left and right child together along with myself. So 0 plus 2 plus 0 gives me 2. And I'll do that same thing for this node 11 over here. And now things get interesting, right? To calculate the total sum rooted at this 11 subtree, I would just return these values to the top. And now I do 4 plus 11 plus 2, which gives me an answer of 17. And if you do a quick spot check, right, this 17 does represent the total sum just in this subtree, right? And we'll carry on over at this 1 node. We know that this is going to return just a value of 1. And now at this for node, I can compute its total sum. And recall that this for node had a left child of 0, right? Because it had a null node. And so when I compute this sum, I get 5, which is perfect. And finally, at the main root, now I bring up these two values, and I compute 17 plus 3 plus 5, and that gives me a final answer of 25, which is indeed the correct answer, right? So that's how we should really think about our recursive algorithms for our binary trees, right? I kind of draw it out. I think about the base case, which is typically, not always, but typically, about the null node. And then from there, I figure out how a parent can compute its result given its children's answers. All right, so if we take a look at the complexity of this, it's pretty straightforward. We'll go ahead and define n as the number of nodes in our input tree, in which case I can see that my time complexity is just O of n, right? We know that we're going to make a recursive call just for every node of the tree, and we're not going to call duplicate nodes, right? We're going to have just one call for every single node, and within any single node, we're just going to do some simple arithmetic, right? We just add roughly 3 numbers together. So it's not like we're going to have like a loop inside of our calls at all. In a similar way, we'll say the space complexity is O of n just because we have that implicit call stack space, because we are going to solve this one recursively. And so we're solving this one in O of n time and space, which would be actually a maximally efficient solution for this problem. And so with that, I think let's head over to the walkthrough video, and I'll show you how to code this one up.